Maybe read about this quiz first and then try it out for a few minutes while we're waiting for the rest to come. Okay, all right. Good morning to everyone. It's a raining day. A lot of you can't make it. Some of you, it's okay. We just start. Is there anyone have problem understanding the statement inside this statement here? Everyone okay with the word subset? And from a set, you pick a few elements, form a new set, is a subset of the original set. Okay? So the idea of clause we introduced last lecture. Okay? So So if you take, so if a subset is closed, okay. So what do I mean by closed here? Closed mean you still stay inside the closed room, right? Okay, for example. So how do you stay inside the same room? Okay, so if you take two elements, okay, from the set, you compose them together. Okay, somehow you have a way to compose them. Okay, then the composition or the product of the two elements is still in the subset. Okay, this means the subset is closed. So where's the composition come from? Okay, typically this composition comes from the original set. Okay, come from the original set. So it comes from the original set. So let's call it X, X star. Okay, X star. So X is our universal set or the original set, and then star is the composition. Okay, so you use the composition to do the composition in your subset. Okay, so meaning you give a composition to your subset. Okay, and this is what we call the induced law of composition or induced operation of star on H. Right? Because by definition, law of composition is defined on the set S. Okay, so a priori H is already a different set. Okay, it's already a different set. So where do I get the new composition from? Okay, so I just get it from the old set. Okay, this is called the induced law of composition. Okay, induced operation. Okay, it's induced from the original set. Okay, does everyone agree already what we have now? Okay, so my question is, does the subset always close? Okay, so if you have a set with a law of composition, you take a subset and then you do the induced, okay, composition again. Is the subset closed? Okay, meaning you take any two, okay, elements, compose them together. Is it still in H or not? Hmm? Yes or no? What do you think? Is this always true? Who said no? Why? If you say no, you need to give a counter example. So what's your counter example? Okay, let's try it. So what's your G? What's your X? Real number with addition or multiplication? Huh? Addition. Okay. And then what is your H? So let H to be a real number without zero. Okay, so this is a subset of R. Sure. Okay. So can everyone see the uh, counter example here? What is going to happen? So we give a counter example. Anyone trying to guess or try already see what is going on? So how to contradict? How to H is not close. One plus minus one is zero, which is not in the subset. Okay. Okay. So you don't take for granted that I take a subset of a group or a set with composition is always closed. Okay. When it's closed, we will call it a subgroup. Okay. So we are interested with those closed subset. Okay, under group. Okay, so induced operation close. Okay, please take note of this. Okay, you don't always get a closed subset. Okay, if it is not closed, then it is not meaningful. So the idea of close is also very important in your analysis. Okay, where you take the limit. Okay, in analysis you take limit. Okay, but in algebra we are close under operation. Okay, close under operation. And in analysis, they want to close under taking limit. Okay. one more, a few more maybe. Okay, a few more. Okay, a few more. So why did I say a minus or division is not important? Okay, so here I want to recall the definition of group. What's a group? What's a group? Anyone can tell me what a group is? Sorry? Okay. It's first of all, it's a set. Okay, it's a set. Very important. In mathematics, either you deal with set, either you deal with function. And there are these two basic things. So every time I give a word, you need to immediately think this is a set, okay, an object or function. Okay, so group is a set, okay, set of elements. So a set is a set with associative law of composition. Okay, so why we care about associative law of composition? Okay, because law of composition only tells you how to compose two things. Because in another name, LOC is the binary operation. Okay, so associative tells you how to compose three things. Okay, so meaning no matter you want to compose the first two first or you compose the last two, is going to give you the same object. Okay, associative. And then this will determine everything else above 4, 5, 6, 7, 8. And if you want to compose 100 elements together. Okay. Do you agree on? If not, if not, we will prove it in assignment. Okay, by the way, about assignment. Assignment I already put on the Moodle. Okay, please check your assignment. Yeah, assignment. So please start soon. Okay. So I gave a question based on the time you have. So I released last Thursday. So please have a look. Even if you don't know how to do, please read. Read every day. Meditate on the question. Okay, meditate. You know what's meditate? Meditate. 冤家, you know what a meditate is? Don't know. Okay? Meditate is a 沉思. No? 沉思. Yeah, did I read wrong? Sorry. Yeah, 沉思. Okay? Meditate on the question. Okay? Yeah. So first thing, you need to have a set of associative law of composition. How about second? Yeah, I don't want from Ziqi anymore. What's the second thing you need to have? Zunling. Huh? Sorry? Yeah, just say it. I didn't hear it. Huh? Commutative. Okay, how about commutative law of composition? We don't put it as a must in our group definition. If it has commutative law of composition, this is an abelian group. This is not a must definition. Okay, this is an abelian group definition. So group have three key properties. Okay. What else? Every element has its inverse. Okay, so inverse exists. Okay, inverse exists for all elements. Still remember what the inverse is? Okay, if you don't remember, you just memorize 2 times half is equals to 1. Okay, so half is the number that multiply to 2, you get 1, the identity. Okay, this is a typical example you have to keep in mind. What else? What's the third one? Identity. Okay, so identity exists. How many identity in a group? 1. Okay, because we proved that identity is unique. Okay, only one identity exists. So you can see that why I say minus or divide is not important. Okay, because of the second line here. Inverse must exist. Okay. So if I define, for example, just now we use an example, R plus. Okay. So the inverse of every element is minus X. Okay. So you see, the minus appear as an inverse. Okay. It's not an operation anymore. Okay. Appears as an element. Okay. It's a how to say? It's a condition of group. Okay. Similarly, how about divide? Okay. If you look at real number time in the multiplication manner, okay, actually this one we need to get rid of 0 to form a group because it's not close like what we see just now if we include 0. Um, so okay, so here the inverse is 1 over x. Okay, okay, because the identity for plus is 0, the identity for multiplication is 1. Okay, so divide becomes an element now. Okay, not an operation anymore. Okay, so that's why we just need one operation is enough, plus or multiply. So in fact, this is how we build our number system here. Okay, so when you are a kid, you only know how to count. Okay, you only know how to count natural number. So these are called natural number because they are natural. Okay, 1, 2, 3, 4, 5, 6. So how to go to Z? Okay, what you do, you go to Z. You do we call a group completion. Okay, how we do a group completion? So this means that we want to add natural number now. Okay, we want to add natural number, but you can see that it is not a group yet, not a group yet. Okay, so how to form a group? I add in the inverse because I need to satisfy three properties, right? Okay, three properties here. I already have associative. Okay, I can plus anyhow I want. Identity exists. Okay, exists in our class because we include 0 into our natural number, but depend on convention sometimes. But how about inverse? Okay, inverse under addition doesn't exist because we don't have negative number, and you also don't see negative in the real world, right? Okay, what is negative? Okay, but when you do payment, you see negative balance. Okay, so when we do group completion, we go to integer. Okay, we go to integer. We complete it as a addition of natural number. Okay, and then what else we can do? What else we can do? Sorry. Already have identity, right? 0. Yeah. So what's the next step in the human advance? So 人类怎么进步？怎么进步？下一步是什么？ What is the next step? Okay, for human to go forward. Eat more banana. You thought you're monkey. Huh? Absolute number, rational number. Okay, rational number. How to get to rational number here? First of all, do you know what a rational number is? What's rational number? Tim born to sleep already, so I call you. So what's a rational number? Okay, P and Q is in integer. Also, P and Q has no, has no. Okay, I think that's enough. Okay, that's enough. Okay, P and Q is in integer. Okay, so how you go to here? So P over Q is what? Divide. So how to produce division? I just say a moment ago. Inverse. Okay, so what we want to put here. So we do another group completion again. Okay. So I make Z into a group. What kind of group? Multiplication. Okay. I make it into multiplication. Okay. So I add inverse into the set of Z with multiplication. So that I form a Q. Okay, we form a Q. So how about I give a notation? So maybe I say group completion as a bar. Okay, let's put a bar is yeah. Let's put a bar, okay? Okay, the bar. What's the next step? So the next step is the real. Okay, but real is a little bit special. Okay, real is a little bit special. I believe you already see it in your analysis class, right? So you found you prove that there's no least upper bound for a set of x such that x squared is less than 2. Okay, so what you are trying to do is you cannot find square root 2. Okay, why we put x squared less than 2 instead of x less than square root 2? Because you don't know square root 2 first. Okay, so that's why we have a square s squared less than 2. Okay. Okay, so maybe we talk about yeah. Do you want to know about C? How to go to C? Sorry? Yeah. How to go to C? Complex number. Are you interested? Interested. So why we go to C? How to go to C? So what are the C elements here? A plus bi such that I square equals to -1, and then A and B in R. To go to C. So to go to C, we will do it formally in this class later. Okay, later in this course. But the idea is you cannot solve s squared plus 1 equals 0 in a real number. You cannot find the root for this guy. Right, you learn the quadratic formula. B squared minus 4ac less than 0, you have imaginary root. Okay? So meaning you cannot find number in real number anymore. So you need to outsource, go outside, and then find new number. So where's this outside? This outside is the complex number. And then which we call algebraically close. Okay, because this number is coming from algebraic equation like this. Okay, algebraic. So just multiply x and then plus or like this. Okay. Okay. Okay, we will revisit the C again. Okay. In future, maybe you will see this kind of notation. We will come back to this. Um, yeah. Okay. Yeah, group. Okay, so you can see that we give this definition a group. Okay, so you might think about a group of people. So how you can become a group? Okay, how you regard a few entities as a group? Okay, so if you want to regard an entity as a group, okay, you can see that we have associative. Okay, associative meaning your three of you, any three of you are equally good. Okay, you get what I mean? Okay, three of you, maybe two of you are good, but the other two is not good with the other one. Okay, then maybe you guys are not a group. You know what I mean? Okay. And identity exists. Okay, so identity exists meaning everyone can refer to maybe the top in the group, okay, or the head in the group. Okay, everyone can get to it easily. So typically in a group, you must have a head. Okay, inverse exists. Okay, inverse exists meaning you can go to this person, go to that person, they are equal. Okay, yeah. So it's not like if I maybe if I form a group with Siyu and Jimbo, okay, but Jimbo only tells things to Siyu, okay, don't tell things to me. Then am I still in the group or not? Huh? I become empty. Okay, so I'm an empty set. Empty. What's empty? What's empty? I know. So what does it mean? Oh, anti me. Oh, okay. So that's why I say if anti me, then I'm not in the group anymore, right? Yeah. Okay. Yeah. So we are not in the group, right? So yeah. So we need to have these associative. Okay, associative. Okay. A billion is even better. Okay. If Jimbo tells stuff to Sui, Sui will also tell stuff to Jimbo. Commutative. Okay. Okay. All right. Let's start with new stuff now. Sure. Okay, let's start with a new period. Okay, so last week we introduced group and then give the definition of group. So one very special definition is the general linear group. Okay, you have to know general linear group. Okay, especially if you go to pure maths. So general linear group is just the set of n by n invertible matrices. Okay, general linear group. Okay, so next, what we're gonna do is we introduce order. So it's like set theory. Okay, after you introduce set, you introduce the cardinality of the set. So what's the cardinality of G? So this is what we call the order. So the order is the number of element it contains. Okay, or the cardinality of the group. Okay? In other words, it's the cardinality of the group. We use the same notation. We denote it as modulus G. Okay, so for now, right, you should think about this modulus G as a what we call a linear functional. If you learn ALA, right, you will see linear functional soon. So linear functional meaning I give you something, you give me a number. Okay, give me a number. Give me a meaningful number here. So the meaningful number here is the cardinality of the set. Okay, you throw me a set. It's not a number yet. Okay, give me a number. Okay, this is the same as a modulus of, for example, -2, -3, or 2. So what are those? Okay, that modulus tells you you are how far from the origin. Okay, for example, modulus of -3 is 3. Okay, how far from the origin? Okay, I just care how far. I don't care you are from the right of it. Okay, so modulus. Okay, next. So very easy one is a group. Right? Okay, what's a finite group? Is if the cardinality is less than infinity, or the order of the group is less than infinity and infinite otherwise. So we can look at a few running examples from uh, previous content. So for example, what is the cardinality of Z? What's the cardinality of Z? It's so long. Cardinality of Z. Infinity, right? It's not finite. Okay, because if you pick M, there's a M plus one always. Okay, it's not finite. Okay, if you pick n, there's an n plus 1 again. You pick n plus 1, there's a n plus 1 plus 1 again. And then so on. You cannot find a finite set of elements. How about Zn? With the cardinality of Zn. Huh? How many elements in n? Zn? Huh? Infinity. Infinity? What are the equivalent classes of Zn? How many number on your clock? How many number on your clock? Oh, 时钟. 12, right? Okay, it's the Z12. Okay, so there are only 12 number on your clock. Right? Although your clock run endlessly, okay, provided the battery is not dead. Okay, so how many elements in Zn? Sorry? So clock is a Z12, okay, Z12 modular 12. You have 12 number. So Zn have how many number? Two? 2n. 2n or 2? 2n. So Z12 has 24 number. You sure? Your clock, how many numbers on your clock? 12, right? So Z12 has 12 numbers, right? So Zn have how many? N. Okay, only have n. So what are the equivalent classes? 0, 1, 2, 3, 4, 5, 6, and then blah, 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 n minus 1. Okay, how about n? N is the same equivalent class as 0. Okay, okay, so you got n. How about multiply? How many elements? Is an infinite group or a finite group? Real number. Infinite, right? Infinite. Okay, because it's already contained Z. Z is already infinite. Okay. Yeah. What else? How about function? The function, continuous function. Okay, continuous function from R to R. Did we consider continuous function is not a set? It's not invertible, right? So we need to pick the homeomorphic one. Okay, so let us write another notation here. So we want a homeomorphism. Who can tell me what is homeomorphism? Who can recall? Minxiu? What's a homeomorphism? Bijective and continuous. Okay, so I put this injection. Wait, sorry. Okay, sorry, I draw something stupid here. So this is onto, and then this is inject. Okay, so we put like this onto. If I put a hook, it's 1-to-1. But we also want continuous. Okay, so this is a homeomorphism. Yeah, two conditions: continuous and bijective. Continuous and bijective. Continuous and bijection. Okay, so what's this cardinality here? Infinity again. Okay, do you have a way how to prove this? Any idea how to prove this set is infinity? So just now I said that there's a Z lying inside R, right? Okay, so you can see that the cardinality of R is strictly strictly greater than Z. Okay, strictly or equal. Strictly or equal. Okay. Yeah. In the what did you learn what the Bernstein theorem was called that? It's a long name. No, you don't know. Okay. It's in the discrete math, I think, about cardinality. If a set is a subset of another set, then the cardinality respect the subset inclusion. Can you recall? I can try and record it. How about this one? Is there any infinite set lying inside this homeomorphic function? What do you think? Tony? Fx equal to x. Sorry? Fx equal to x. It's just one function, right? Yeah, I want infinite of them. So, sorry? Fx equal to x plus n. Okay, fx equal to x plus n also work. Or fx equal to n. Okay, so you can see that fx equals to x plus n or xs equal to n. Okay, so x equals to n. Okay. N could be a real value really, or you fx equals to n. So you can see that my set here, this set here, I'm creating sequence already, sequence of function. Okay. Sooner or later, you will see it again. Sequence of function, okay? Fx equal to n. Fx equal to x plus n. Okay, how about GLN? GLN. Okay. For each n, what's the cardinality? For each n. Also infinity. Okay, what is GL1? What is GL1? What is GL1? 1 by 1 invertible matrix. What is that? It's just real number. Okay, it's just real number. So what's the difference here? Maybe you just put an extra bracket there. 1 by 1 invertible matrix. What is this? This is really just a number. X. Okay, so it's the same as a real number. Yeah. Oh. Sorry. Reset 0. Okay, set 0. Correct. True. Thank you. So Rx. Okay. Except 0. Because 0 is not invertible. Okay, so maybe let's make this very clear. 0 is not. Okay. Okay. So you got infinitely many elements, right? You take away one, it's still infinite, right? Combine the argument. So if you have infinitely many objects, you take away one object, you are still infinite. Okay, so this is the same idea as the sequence we studied last time. Okay, you have sequence, okay, converging. Even though the finitely many term doesn't converge, the last few term converge. Not last few, the last for the n large enough, converge is enough. Okay, for the conversion, you don't need to care about the finitely many terms. Okay, because it is still infinite for n large enough. Okay. How about I try one trick here? Let's say I change my my number that can put inside my matrix here. Okay, let's look at a 2 by 2 matrix with Z2. What is Z2? How many elements in Z2? 2. Okay, so there are only two possibilities you can put in these four boxes here. So try and guess how many. What's the cardinality of the set here? Huh? Sorry, two. Which are the two? 0, 1, 1, 0. Only two. Okay, how about the other choice? 0, 0, 0, 1. Huh? It's not. It's not invertible. Okay, not invertible. Okay, so you can check that. Those that are invertible is just only these two. Okay. Yeah, and then first one is the identity. So this is the GL2Z2. Okay, so yeah, so this is one of the object will appear in the research field. This thing if you follow who is that? Think Ma Jiajing staff is working on this kind of thing. GL and with different number field. Okay. Okay. Any question about the order of a group? Why we care about order of the group? Because there's some classification of finite, but a simple group. Okay. Later we'll see what's a simple group is. Okay. Later I will show you. So finite group and infinite group. Okay, let's introduce some notation. We don't want to draw the star again and again and again. Okay, so let us drop the star. Okay, if we say the composition of A star B, we just write as how we normally write the multiplication of xy. Okay, so we just write A and B concatenate to each other. Okay, right side by side. We don't put star anymore. Okay. Okay. So if I don't put star, you need to ask what is the composition on this object. Okay. You need to always check because I'm trying to reduce work. Okay. Let's check some interesting property. So one property is each element in the group also has a unique inverse. Okay, has a unique inverse. Okay, I give you 5 minutes. Okay, you discuss with your friend how to prove this. Okay, one idea is you can try and see how it prove for the identity elements. Yeah. Okay, I give you 5 minutes. Discuss with your friend. And discuss with your friend how to prove this. Yeah. Recall how to start a uniqueness proof. Okay, please take your time to practice proof in class. Yeah, with
inverse of 中文你帮我翻译一下。
可以是可以，but 你以后要练习，OK？so he is asking me to translate for him. He want to speak in Chinese Mandarin, but 你要慢慢练习，OK？我可以帮你翻译，但是我不可以永远成为你的翻译官，可以吗？OK，可以，你来。
E 等于 B 运算 A 运算C 就等于，然后用那个结合律，然后 B 那个 A
先
B 和 A 然后那个把括号移到那个 B 和 A， 然后就是 E 运算 C， 然后就等于 C。
Yeah, even though you speak Mandarin, I think I don't fully understand, right? 什么是运算一啊？Oh, okay. Yeah, that's why. So you see, our language is different, so I don't understand. So, okay. So, okay, let's start again. So, you start with what? You set B and C as the inverse of what do you call X? Okay, of A. Okay, so let A be any element in my group. And let's call my group G star. Okay, so okay, we set this. Okay, so what we do next? B is equal to B star E. Okay, so E is the identity, right? Okay, good. So this is since E. Okay, since the identity exists, in our group G star. Okay, what next? Yeah. A star C. Okay, A star C. Why can we do this? Does anyone understand why he did this? C is the inverse of A. Okay, so by assumption, okay, so this is assumption. By assumption, C is inverse of A. Okay, next. What can you do? Can we straight away do that? Can we straight away compose B and A now? Are they in the same bracket or not? 可以直接乘吗？为什么？ No. Okay, it's a group is correct, but it's not direct. So they are not in the same bracket. 他们不在同一个括号里面，对吗？怎么办？添加 we need to use associative. We need to use associative. All right. So we need to move the bracket to the same place. I mean, not the same place, the place that we want. Okay. So only now, we can use the assumption again. Okay, use the assumption again. So this is by associative of G star really. So this is E times C. Okay. So what is E times C? Is still C. Okay. So we have used a lot of things here. Almost all the definition. But I mean, there's one thing you haven't used, right? One definition, one part of the definition you haven't used. What's that? You use identity, you use inverse. What else you haven't used? Sorry, you use identity, okay, you use inverse, you use associative. what it meant is there's one key fact you haven't used. So what's the word appear in our proposition here? We care about uniqueness. We also care about existence. Okay, so how do you start with this line here? Set AB as an inverse of A. How can you just set like that? Straight away pick two, pick any two. How to pick? Does it always exist? Exist or not exist? Sorry? Sorry? G is group, and then what about group? G must have. So I haven't recall here yet. So let's go back. So G must have Y for all x such that xy or yx equals to identity. Okay, so this is the statement for the existence of inverse. Okay, so existence. So by group, you already have existence, but you don't have uniqueness. Okay, so this is what we're going to prove just now. Okay, so existence. So what? So existence is okay. Existence of inverses is given by the definition of group. That is given by the definition of group, and then we just prove that. We just prove that the inverse element is unique. Okay. Okay. So existence, uniqueness, Okay. Very often we want to solve this problem in mathematics. Any question? Any question before we take a break? No. Wait. Wait for the response. Any question before we take a break? Okay. No? Okay, so let's take a break until 10 and we'll come back. Ah. 上面那个 matrix 我觉得很哪一个？这个 matrix 有两个？我是讲一个吗？这个。然后另外一个是1 0 OK， try 看了。这个的影子是 swap 减 AD 减 BC。OK， 它是他自己的 inverse。但这个应该也是他自己的 inverse。觉得你对。我一开始想说以为也是就这个。OK。嘿，不然我们 make it OK 可以。然后我再跟他们讲一下。谢谢。等一下拿去吃。我有吗？大吃什么？真好现实派。什么？因为这里的。不是嘞，不是。哦，所以这个不是这个是什么？这个不是这个是。OK。 叫我想错东西，我也是那个 characteristic function。OK，可是这个呢？这个是什么
那突然感觉这一条是
？OK，等下我 check 一下。OK，等下我刚刚没讲
前面那个是的，上面那个
这个，还有这个。
好像这是什么？
什么是什么？
因为他讲这个是一个 group，我要讲 F 是，然后我这边讲讲讲一阵，它是一个 group，因为你跟人说你一定要是做盘子，然后总之那四个东西吧。
呀，
然后我那时候是我在那边想
就是他，你要知道他讲 define，他讲 define，要 define 那个，要 define，要讲 define 这个 addition of function。
addition function 这个就是我们好多事情。identity 那个没有问题咯，肯定有的。
对嘞，所以是什么问题？
我要讲是它是 close 的，
因为你还是个 function 呢。
哦，我只是想要这
对啊，
一个 function 加
还是个 function 呀。
哦，
因为它 f 是一个 function，
哦，
对不对？对不对？对。
对。
什么？啊呀，
assignment 那个delta 是什么呀？这个版式，我就想对，我是想坏了。
anything 啊 anything 哦 anything，
可是不应该是
不 care 不 care
我把它当个版式，可是应该是
不 care don't care
6个吧。
I don't care。
没有，它的 inverse 这个是减一，
但是减一在你这 in 也是
可是这个没有关系啊，我叫 invertible 刚有 invertible 里面还有 inverse 是来
没有我讲减一的话，在 Z2 里面是一。现在我看一下我能不能这要 D， 哎呀去，我忘记了 D 跟 A 交换，
然后减 B 也是
AD 减 BC。
011个
没有想，现在我想直接 proof 根本直接 proof 应该要从这边开始打 AD 减 BC 不可以是0，所以 AD 减 BC 只可以是1，所以有几种情况是 AD 减 BC 是1。
什么呀？1.0 1.1哦，
因为我的
要感觉到1.0 1.1，
哎也有可能是减1 ，OK， 有可能是0，有可能是1，或者有可能是减1嘛，我的 AD 减1，但是减1跟1是一样，但是我们不要0，所以只要1。
对，所以怎么？所以就1.0或者0.1啊
OK， 所以1减0或者0减1咯。OK，
这样子这个减一减一
either AD 是一样，或者 BC 是一样咯，对不对？AD 一样，或者 either AD 一样，或者 BC 是一样，对，没错。
你这里3个配对3个配对，
或者也有1乘0，1乘0乘1，
所以6个可以。没有啊。
所以可以啊，没有问题啊。
6个可以。
或者0对吧？或者0乘0，对不对？1乘0，0乘1或者0乘0 ，OK。所以 AD BC 0001，所以这个是不是包含了刚才这个数据 ？OK。
4个嘛，然后还有0 1个110。
所以还有这个不是111这是不啊？
这个关闭，这个在下面。这个也可以。
这个要上去。
这才能可以。
你看一下是不是这边全部 cover？
对。
1、2、3
456，1 2 3 4 5 6。OK。哎，每次没有出东西就是会错。好。
testing. Okay. Okay, is everyone back yet? Okay, something we want to correct first before we proceed. Okay, good. So just now, someone realized that this fx equals to n, right? Is not objective. So we can forget about this. But the following here is objective. Okay, so why I think about this constant function? Because constant function is very important for you to build to estimate your continuous function. Okay, so you can approximate your continuous function using constant function, or sometimes we call the characteristic function. But sadly enough, it is not bijective. Okay, although it's continuous, it's not bijective. Right? Okay, it's continuous but not bijective. Okay. Yeah. Okay. Okay. Next, this question here. I also make a mistake here. Okay. At first, when I thought about this question, I also only thought about these two. Okay. But I didn't show you the proof, right? I just tell you these two work. Okay. So typically, this is what happened in mathematics. So if you don't prove it, and most likely you are wrong. Okay. So we are wrong now. Okay. Oh, I'm wrong. Okay. I'm wrong. Okay. So how to find them? Okay, how to find them actually? Okay, let me show you how to prove this. Okay, so this is the power of abstraction now. Okay, I'm going to prove this. So I want to end the dispute of whether it's 2 or 6. Okay, so I need to prove it whether it's 2 or 6. So how am I going to prove this? Okay, so I need to take a matrix from a GL to Z2. Okay, so to understand this proof, you have to understand the object GL2Z2. What's GL2Z2? It's the set of 2 by 2 matrix, okay, with the entries in Z2. Okay, so you only can put 0 or 1 into your matrix. Okay, so typically a typical M will look like A, B, C, D. Okay, A, B, C, D satisfy what? A, B, C, D are all in Z2. Okay. So is identity in here? In here, right? Okay, identity is in here. In particular, it is just the same identity as usual, 1001. So apart from identity, what else you have? Okay. So now we are going to do abstract stuff. So in group, what's the definition? As inverse must exist for every element. Okay. In particular, this M must have an inverse. Okay. So to make sure M has inverse. Okay. So what we need to do? Okay. This is a 2 by 2 matrix, right? Do you know how to find the inverse of a 2 by 2 matrix? What's the formula? Multiply by what? 1 over determinant AD minus BC. Okay, multiply by what? What is this? What's the matrix become here? A and D swap, and then B and C put a minus. Okay, but when does this matrix exist? Still remember or not? When does this exist? Michelle, when does this exist? Determinant is not equal to 0. So you see, why last time we said that invertible matrix must have non-zero determinant? It's exactly because of the formula here, right? Okay, so we go into the details now. So we need to make sure AD minus BC is not 0. Okay, so first we need minus BC is not 0. Okay, so in our case here, ADBC can only be 0 or 1. Okay, so if you multiply 0, 1 plus together, what kind of number you can get? If you add or multiply number in 0 and 1, what sort of number you can get? Either 0 or 1. Okay, so if it is not 0, then AD minus BC must be 1. Okay, or negative 1. Okay, or negative 1. Maybe or negative 1, but negative 1 in Z2 is just okay. In Z2 is still 1. Z2, okay. So in Z2, but in Z2, minus 1 is the same as 1 more. Okay, so really we just have 1. Okay. Is it okay? Okay. Okay, so really we only have 1. I put inside. Z2. Okay, so minus 1 and 1 is the same in Z2. Okay, right. Okay, we only care about Z2 entries. Okay, make sense or not? Does it make sense? So for example, right, if you cannot reimagine what I say, so for example, I put minus 0, 0 here. This is the same as 1, 0, 0, 1. Okay. Okay. So minus 1 and Z2 is the same. Okay. And agree? Agree. Okay. So now we only care about how to get AD minus BC equals to 1. Okay. And then choose from 0 and 1. What kind of possibility you can get? What kind of possibility you can do? What can you do? How to get 1? Okay, so maybe we don't break into ADBC first. Okay, what minus what equals to 1? 1 minus 0 equals to 1, or 0 minus 1 equals to 1. Okay, be careful, we are in mod 2, so okay. Okay, so be precise. I will write mod 2 here so you don't confuse. Okay. Okay. So there are 2 possible ways here. So now break into AD and BC. So what multiply what you can get 1, what multiply what you can get 0. So let me move this guy. Okay, so yeah, so let's write down AD. So what are the possibility you can have? You can have 1, 1. Okay, and then here you can have 1, 0, 0, 1, and 0, 0. Correct? Okay, how about the second possibility? Okay, so same. Okay, you will get 1, 0, 0, 1, 0, 0. And then on the other side, you can get. Okay, so let's draw out these matrices, right? These matrices. Remember, these are representing the A, B, C, D in our matrix. Okay, so what sort of matrix you can get here? So AD is 1, 1. So we have these. Okay, we have 3 of them. Okay, BC, we can get 1, 0, 0, 1, or 0, 0. Okay, so this is the first three we get. How about the second choice? We'll get 1, 1 on BC, 1, 1, 1, 1, 1, 1. Okay, and then AD will get what? 1, 0, 0, 1, and 0, 0. Are these all different matrices or no? Are these all different matrices? Are they different? Different, right? Okay. So probably these are all the so these are all. Okay. Let's recap how I did these just now. So mathematics is like this. Okay. So somebody say this is correct. Okay. Somebody say this is wrong. Okay, wrong. So you come here and say, I produce another 2. I got 4 already. Okay, maybe we got 4. But just now, Jinko said, I can produce another 2. Whoa, 2 more again. Oh. So when does this process will end? Okay, so we end like this. So we have one condition to check how the inverse exists. Okay, to satisfy this inverse exists, these are the only possible choice. Okay, these are the only possible way to get it. So we end here, no more already. You cannot have another person tell you that there's a few more. Okay, provided what? This proof is correct. Okay. Yeah. Yeah, provided this proof is correct. Any question about this proof or not? Question about this proof. So we are trying to exhaust all the possibility. Yeah.
So the binary operation is multiplication.
Matrix multiplication. Yes. Okay. Yeah. So this is why we are obsessed with proofs. So we need to check whether something is right or wrong. Okay. Question? No. Okay. Continue. So let's continue. Okay. So let's continue. So next proposition is cancellation law. So cancellation law, you should be quite familiar, but maybe you don't phrase it in this way. So let's see. So in a group, if xy equals to xz or yx equals to zx, okay, we can just cancel x from both sides. Right. This is your high school algebra, right? -2 from both equation. Okay, so what are you doing really? What are you doing? What you do is you just multiply inverse on both sides. Okay, multiply inverse of both sides. And why inverse exists? Because it is a group. Similarly, if you have xy equals to x or yx equals to x, then you can remove x from both sides and you will check that the only thing that satisfies the equation is the identity. Okay, nothing else. Okay, so this proof I will left as an exercise. I will complete it. You can check with me later. Okay, left as exercise. So why this is important? This is actually not true always. Okay, if it is not a group, especially. So this cancellation law doesn't need to hold. Okay, doesn't need to hold in general when the especially when the element is not invertible. Okay, so for example, where? So for example, in Z6, okay, if we consider 3 times 2 and 3 times 4, okay, what are both these equal to? 0 mod 6. Hey, by the way, I want to check whether you guys learn this modular arithmetic in discrete math or not. Got GCD, got, huh? Okay. Later soon we'll see those things. Okay. Euclidean algorithm. Okay. Extended Euclidean algorithm. Okay. Okay, good. Sure. So you see, both of them are equal to 0 mod 6. Can I just get rid of 3 or not? Can I just get rid of 3? If I get rid of 3, what happened here? Equals to 4 mod 6, which is contradiction, which is wrong. Okay, so you cannot just see both of them have the same thing and then you throw away. No, it's because you have inverse. Okay, it's because if you have inverse, you add inverse to both sides or multiply. Okay, depend on your law of composition. Okay, so you cannot just remove 3 from both sides. Okay, unless it is invertible. Okay, so this is very important. Important later. Yeah. X must be fixed. Yeah. X, wait, what are you trying to say? Sorry. Here, X is a fixed X. So my point here is when the X is not invertible. So meaning 3 is actually not invertible in Z6, where the law of composition is multiplication. Okay. So what am I including here is 3 is not invertible Z6 multiply. Okay, so we have these 2 equals to 4 things if you just cancel 3 from both sides. Correct? Okay. So do you guys know when M is invertible in Zn in the multiplication sense? Did you guys learn this? Well, learn this. So let me give the statement here. So when does M invertible in Zn multiply? When does this happen? You know? When does this happen? When so is when M is not 0 and M is co-prime to Z to N. Did you guys prove this? This or not? Ever prove this? No? You don't remember? You don't remember? Okay, if you don't remember, right, I'll remind you next time. Okay, but please remember this statement first. Okay, when I gonna use this statement, I'll try and recall for you. Okay, so only when M is co-prime to N, okay, then M is invertible. So in this case, what does it mean? So you can deduce what? When is Zn a group? When is Zn a group? When every element is co-prime to N. So when does this happen? when does every element in Zn co-prime to n? For what n does this happen? Only when? Only when n is a prime. Okay. So only Zp cross is a group. Only Zp is a group. Okay. So prime number is the one. What's the definition of prime number? It's the number that divide itself and divided by 1. Correct. So everything else should be co-prime to it. Correct. Okay. Yeah. Okay. So only when n is a prime, then Zn is a group under multiplication. All right. Good. Okay. We will come back again to this. Okay. When I'm going to use this, then I will record the proof for you, and then you will see. Okay. So we're gonna do some technique. Okay. You like to calculate, right? Okay. We're gonna do a lot of calculation. So we'll introduce a multiplicative table for a group. By the way, when I look through your syllabus, right, I found that some parts are quite redundant or repetitive. Okay, because most of them are example. And then as what I projected, the syllabus is only designed for 3 hours at first. Okay, but now we are 4 hours. So maybe if I cover faster, we might do more topics. Okay. Yeah. So in that case, right? So maybe I'll jump some part, or so if you want to do pre-reads, for example, maybe I will put in advance what you need to read before coming to the class in the week. And also I put out the tutorial question. Actually, if you realize, you can try and do the tutorial question and then you let me check. Okay, and then I can give you feedback. I don't think I will spend time to prepare the solution. Okay, I don't want you just to sit there and then see my answer and then read like that, because I already provide a lot of question and solution past year for you. You can do that for those. Okay, so if you're gonna do this solution, this tutorial, there's no solution, you can give me check. I give you feedback, and then maybe I can share this solution to your friend also. Okay. Okay or not? Okay. So I think you also use your work to change my work. Okay, so we exchange work. Can or not? Does it make sense or not? Okay, you work and then I also work. Okay, not just I work. Okay, and you just sit there and then enjoy. Right? Okay, you work, I also work. Okay. Yeah. Okay. So technique. Okay, so we're gonna introduce this multiplication table. So if you look at some textbook, right, they will call it a Cayley table. So this Cayley are quite famous in group theory. So there's a famous theorem about every finite group. Okay, later we will introduce it. So this Cayley table here. Okay, Cayley. So what should we do? Okay. So first, what you do is you fix your first row and the first column. Okay. What is typically in your first row and first column in your spreadsheet? If you're gonna use Excel spreadsheet, what happened to your first row or first column? Do you just start with your data? What do you start with it? A list of properties, right? Okay, or a list of name first. Okay, so we do a similar thing. So the first row in our case is simple. Okay, first row and first column is the same. Okay, we just list down all the elements in the group. Okay, we just first list down all the elements in our group. Okay, so it's a symmetric table. Okay, and then we need to have some name for all the columns. Okay, so let's label all the table entries. Okay, by ij. Okay, where I is the row, J is the column. Okay, in a lexicographical order. Lexicographical order. Lexicographic order. Okay, from the top left corner. Left corner. Okay, and so what we're gonna put inside this ij column here is exactly the product of two elements from the from ij and j one. Sorry, so let me write down. So the entry. Okay, so what's the entry of ij here? Okay, what we're gonna label this entry is the product of two elements in I1 and ij. Okay, so you might think that, hey, why you don't just straight away draw to me? Give me so many instructions, one so abstract. I don't want to listen. Okay, I just gonna see what you're gonna do. But a very important thing in mathematics is you need to learn the instruction. Okay, I was also like that last time. Okay, but I only realized after I did a PhD. Okay, after PhD, right, I realized that I need to read some manual before I use some electrical appliance. Previously I also think that this manual so thick. What's the use of this? I just try it out myself, right? But why is it the manual is very important? Because the manual tells you how to use the applicants, okay, without just trying for fun, okay? Because the price of just trying will be you break the appliance, okay? You will break the appliance, okay? So this is the manual, okay? So try to learn how to read this instruction. Okay, so now I'll tell you how to read this instruction here. So this is one of the things you will get from doing mathematics degree. Okay, so let's start with Z3. Okay, so for example, let's start with a small group Z3. Okay, so how many things in Z3? Okay, we still remember how many things in Z3? 3. Okay, good. 3. Okay, so there are 3 elements in the Z3. So what are these elements? So first, I list down all the elements in the first row and the first column. So what are these elements here? What do we call this element? Sayed, what are the elements inside Z3? 0, 0, 2, 0, 1, 2. Okay, so they are not just number, they are set of equivalence classes. Okay, 0, 1, 2. Okay, 0, 1, 2. So you see, I got how many entries that I need to care? Okay, so how many entries I need to care here? Okay, so I need to care about 1, 1, 1, 2, 1, 3, 2, 2, 2, 3. Okay, so let me use something else maybe. So I use 1, 1. Okay, we have a 1, 1 entry. So we label the table entries using ij. So 1, 1, and then 1, 2, and then 1, 3, and then 2, 1, 2, 2, 3, and then 3, 1, 3, 2, 3, 3. Okay, so what are the things I need to put inside here? Okay, what is the thing I need to put inside here? It's the product, okay, product of two elements in J1 and J1J. Okay, so you immediately see something weird here, right? J1 should be something here. Okay, and then ij should be something here, but there's nothing here. So I think we should start with 0 in this case. Yeah, let's start with 0. So we start with 0. If I say first row, it starts with 0. Are you confused? Okay, maybe we change this to 0 column and 0 row. Let's start with 0. Since our natural number start with 0. 0 column and 0 row. Okay? Okay, so that we have a consistent change here. Okay, otherwise we need to start with 2. Okay. Yeah, there are a few conventions here. So what do you think? You want to start with 1 or start with 2? Or start with 0? What do you think? What do you think? Just let me decide. You want to start with 0 or start with 1? Start with 1. Okay, let's start with 1. Let's start with 1. Okay, in this case here, so let me think. So in this case here, this row is 1. Let me think. So this is a 1, 1. This is a 1, 2. This is a 1, 3. This is a 1, 4. And then this is a 2, 1. This is a 2. Sorry, this is E1. This is a 4, 1. Okay. And then we need to add everything up here, right? So here is a 2, 2. Here is a 2, 3, 2, 4, 3, 2, 3, 4. And then 4, 2, 4, 3, and then 4. Okay, so we label all our table entries with this IJ already. Okay, so what should we put in these 2, 2, 2, 3, 2, 4, 3, 2, this? Okay, the number that is greater than the entry for I and J. Okay, greater than 2, and then J greater than 2 as well. So IJ greater than 2. So I'm trying to complete my instruction here. So IJ greater than 2, okay, is the product of what? Two elements in I1 and IJ. Okay, let's check this. So you see, 2, 2 here, okay? 2, 2 here is the product of 2, 1 and 1, 2. Okay, so if I take product of 2, 1 and 1, 2 here, what do I get? Okay, let's make this bigger here. Okay, so here is 0 plus 0 here. 0 plus 0 here. Okay, how about I make so 0 plus 0 here. Okay, how about 2, 3? How about 2, 3? So 2, 3 is the product of 2, 1 and 1, 3. Okay, 2, 1 and 1, 3. So 2, 1 and 1, 3. Okay, so it's 0 plus 1. Okay, yeah. Okay, so how about 2, 4? 2, 4 is the product of 2, 1 and 2, 1, 2. Sorry, 2, 1 and 1, 4. Okay, so in this case, you get 0 plus 2. Okay, so from here, I think you can deduce the pattern already. Okay, so what we get is we just take the intersection with the row and column, the elements from the intersection of row and column. Yes.
The plus
Require a head. Yeah, we can draw the head on, or this plus is just the head we defined last time. Okay, so if you want to be clearer, you can put a head. Okay. 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 Yeah. Okay. So yeah. So try and complete this table, and then we'll check whether we get the same table or not. Okay. You try and complete this table. Complete this table, and then see if we get the same table later. I give you about 2 minutes, and try and complete this table here. Yeah. Try and complete this table here. And try and complete this table. See if we have the same calculation or not. Sorry? Yeah, it's the same. No, I'm just trying to compute the final answer. Okay. Okay. How about this? Let me call this. Hey, I haven't take attendance, right? So let me take attendance and then we will start. Venus. Okay. 乐天. Yeah. 宇哲. Okay. 上 not here. 诗雨. Jing Seng. Yeah. 顺林. 海人. 金波. 七. Okay. 华英. Oh. Okay. Hello, testing. Huh? Hey, why got light? Use to sharp. I need to use marker already. Aircon. Yeah. Okay. Let's continue with the name taking first. Who else? Pishon or Pishon online. 英奇、何怡、雪岩、嘉业、嘉业 I think online. Is it online? Sick. Okay, 李凯 ，Yeah， 袁家、文硕 ，Yeah， 一定 ，near the back， 玉维，燕博，陈烨 ，OK， 林晶 ，Yep， 董杰，宜州 ，Yep， 董杰，宜州 ，Yep， 定宇，柳晴，真诚 ，Yep， 硕宁 ，OK， 古力，子倩，德先，莹莹 ，Grace， Grace. Grace, right? Okay, I first time see you taking off the mask. Didn't recognize you. Syed. Jiawen. Mingxiu. Michelle. Brian. Hey, Ellie, where's Ellie? Don't know. Missing in action. Okay. Xue Mei. Ziyuan, I think so, yeah. Rylan. Is it Rylan or Stephen? Rylan, both can, okay. Yan Ke not here. I think he just joined. Zeri. Yeah, Zeri. Okay. Okay, good. Let's continue with our traditional style. Okay. How about the other classroom? Also got problem. The other classroom. You don't know? Okay. It's okay. Okay. So let's check whether we got the same table or not. Everyone see the size or not? Can see the size? Need to be bigger. I think need to turn on light now. Yeah. Open up. Okay. All right. So you should get 0, 1, 1, 2, 2, 0, 0, 1. Is it the same? Same or not? Okay. 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 Good. So maybe we can make this bigger. So if we're gonna make this bigger to 4, okay, let's add another one. So 3, 3, okay. So what do we get here? Okay, see if you can do quick calculation here or not. Let me get my eraser. Yeah, you can try, and then I'll give answer. So let's try this. So you get 3, 3, 3, 3. Okay. Zero. Okay. Yeah. Yeah. Well, you can see kind of like increasing by 1 on the diagonal, and then repeat the pattern again. Okay. Yeah. So this is a pattern you see. Okay. So this is a group of how many order? Order what? 4. Okay. So this is a group of order 4. So I'm going to introduce another group of order 4, which is a Z2 cross Z2. Okay. And then with addition as well. Okay, with addition as well. Okay. So what are the elements here? Z2 cross Z2. It's a product set, right? Okay, it's a product set. And then you only have 0 and 1 here. So you have 0, 0, 1, 0, 0, 1, and 1, 1. Okay. And then you can try and add them together using this table here. Okay, try and add them using this table. Okay, what do you get? You can try and compute while I'm writing here. Okay, and then check whether we get the same answer. Okay. So 0 plus 0, 0, 0 plus 0 is still 0, 0. Okay, so how should I add? How should I add here? I should tell you how to compose, right? Where's the LLC? Where's the LLC here? So what is AB plus BC? Sorry, maybe just put C. You want to see up to here? Can I? Yeah, can see or not? Still can see. Okay. So AB plus CD, how to add? Components wise, okay? A plus C, B plus D, components wise. Okay, so this is what we're gonna do here. So you can see whether I did the right calculation or not. Okay. Okay, so why do I care about these? Can you realize anything from these two? Or too many figure here? Too many figure here? How about I abstract this element here? So maybe I call it E, A, B, and C. Okay. So let's record this multiplication table differently. So E, A, B, C, A, B, C, E, C, C, E, B, A, E, A. Okay. So now can you compare this table with the first table here? Do you see any difference or not? Where's the difference you first see? Huh? The diagonal. Okay, so the diagonal here is 0, the identity 2, identity 2. But there is all identity. Right? Okay, how about other places? Are they the same? So for example, this part here, right? So so first part here is here. Okay. Maybe just these two, right? Okay. How about this guy? Should be identity become B, and then here identity become B. Okay. So seems like there's a difference here, but how to prove this? Okay. Actually, these are the only two different groups of order 4. Okay. I put inside your assignment last question is to prove that these two are not the same. But we haven't get to the tools yet, but I want you to have these ideas sink in. These two are different. Okay. Maybe you can think that, hey, how about I swap the position? They are different by these 4, right? I can just swap the position so that it resembles that table, right? Do you think so? Do you think so or not? Because the difference is 2200. Here also have BBEE 2200. Maybe I swap position. Maybe I can get to that arrangement, right? But you can't do it. If you swap one of them, the other composition will swap as well. Okay, so how are we gonna prove this? How are we gonna prove this rigorously? Okay, the tool we're gonna introduce will be hopefully next week, next Tuesday. Hopefully, we will touch this. Okay. Okay or not? Okay. Any question? If you don't believe, right, go back and try. See if you can swap this B up or not, and then swap this E down, and then such that all the multiplication entry are the same. Okay. Okay. But the fact is there are only two groups of order 4, and these are the two. Okay, any question before we break? I think we don't want to continue more because not convenient to start new stuff. Any question about multiplication table? So you should think that this is only very good for finite group, right? If infinite groups, how you're gonna list all of them down? Okay, yeah. Any question? If not, Jingbo bring some fruits here. If you want to take some and try it, you can. Or if we go to lunch, also can eat this together. You know what this fruit is? What's this fruit? Kimpo. Kulansat. Okay, you can try this. This is a tropical Malaysian food. Yeah. Okay. Or later we can eat together if we go lunch together. Okay. Any question? If not, see you on Wednesday. Wednesday. Yeah, Wednesday.